In the world of software, there's one question that gets asked over and over and over again. And the answer, almost always, involves this really clever trick, giving up a little bit of order to gain an incredible amount of speed. Today, we're going to dig into the hash table, not as some dry data structure from a textbook, but as this brilliant hack that pretty much powers the modern internet. Let's get right into it. Just think about it for a second. Almost everything your computer does, it boils down to this one simple question. When you log into a website, have I seen this username and password combo before? When you're browsing the web, is this picture already stored in my cache? It's just this constant, relentless check of identity. And that's exactly why we're here. Because when you need the absolute fastest possible answer to that question, have I seen this before? The hash table is the tool you reach for. It is the sledgehammer for this very specific nail. So here's how we're going to break this all down. First, we'll look at how they turn an identity into a physical location. Then, we'll talk about what happens when things inevitably clash. We're going to bust the myth of instant speed, see where these things are hiding in the wild, and then we'll wrap it all up with the really big idea, the power of making a good guess. All right, first up, let's get past that basic textbook definition and really get to the core of how a hash table actually works. It's all about this magic trick of turning what something is into where it is. Okay, so this slide really shows the two different ways of looking at this. On the left, yeah, that's what you learn in school. It's a fast way to connect keys to values. Simple enough. But the real story, the magic, is over there on the right. A hash table isn't some perfectly organized filing system. It's a betting system. It makes a bet that it can instantly transform the identity of something into a position in memory. And here's the bet itself. It's a two-step process. First, this special function, the hash function. It takes your key, let's say it's a username, and it turns its meaning into a number, into pure math. Then, step two, the system basically gambles. It bets that all those numbers it generates will be spread out nice and evenly, kind of like throwing a handful of seeds across a field and just hoping they don't all land in one big clump. And this right here is the most important part. The entire speed of a hash table, everything it's famous for, rests on this one bet paying off. And you know what? Most of the time, with a good hash function, it does. But it is never, ever a sure thing. And that little bit of uncertainty, that's the source of all its complexity. So what happens when that bet doesn't pay off? What happens when two of those different seeds land in the exact same spot? Well, that's when we get a clash, or what engineers call a collision. A collision is super simple to understand. You've got two totally different keys, maybe John Smith and Sandra D, and they both get crunched by the hash function and end up pointing to the exact same spot in memory. And I want to be really clear about this. This is not a bug. It's an unavoidable mathematical certainty. It's like having people in a classroom. Eventually, two are going to share a birthday. So, how do we deal with this? Well, there are two main strategies, and you can see them here. On the left, you've got chaining. The idea is if multiple things land in the same spot, you just start a little list there. It's like putting several files into the same folder. The strategy on the right is called open addressing. It's even simpler. If a spot's taken, you just look at the next one over, and then the next until you find an empty one. Easy. And this really gets to the heart of it. The goal isn't to eliminate collisions. That's literally impossible. The goal is just to make them so incredibly rare that they don't really matter. The speed of a hash table doesn't come from perfection. It comes from playing the odds and playing them really, really well. This brings us to one of the biggest myths you'll hear about hash tables, that they're instant. You'll often hear this described with the fancy term O of 1 or constant time. All that really means is that it should take the same amount of time to find one item, whether you have 10 items or 10 million. But that's not the whole story. See, the actual speed you get in the real world depends on a few things. How full is the table, for instance? We call that the load factor. Is your hash function actually doing a good job of spreading things out? What does the system do when the table gets too full and needs to be resized? And this one's really important. What if someone is trying to break it by sending you data that they know will cause a lot of collisions? This slide really shows the two extremes. On the left, you've got the average case, the dream scenario. Access is nearly instant. That's our O of 1. But on the right, that's the nightmare. If everything collides, your super fast, amazing hash table suddenly becomes just a slow, boring list. You have to check every single item one by one. We call that O of n, and trust me, it is painfully slow.
Okay, so now that we understand the theory and all the risks, where do we actually use these things in the real world?
The short answer, pretty much everywhere. They're in the web caches that make your favorite sites load in a flash. They're deep inside the databases that power, well, everything. They're used to check your passwords, to find duplicate files on your cloud drive. Seriously, once you know what to look for, you start seeing them all over the place.
But of course, nothing in life is free. As this table shows, for every single benefit, there's a cost. You get that incredible lookup speed, but you totally give up any kind of order. The items are just scrambled in there. It's got a simple interface, but that simplicity costs you a little bit of extra memory. And yeah, it scales really well, but you always have to live with that tiny little risk of hitting the worst case slowdown.
And all of this leads us to our final and maybe most practical section. How do you decide when this powerful but kind of blunt tool is the right one for the job? Okay, so here's the bottom line. You use a hash table when all you care about is checking for existence, like, is this user ID in our system? And raw speed is your number one priority. You do not use it when you need things to be sorted, like for a high score leaderboard, and you should definitely avoid it in situations where a sudden, unexpected slowdown could be catastrophic, or if you think an attacker might try to force that worst case scenario on you. And that really brings us to the most powerful way to think about this whole thing. A hash table doesn't perform a search in the way we normally think about it, looking through things one by one. It makes an educated guess. It uses math to guess the exact location of the item you're looking for. And when that guess is right, which in a well-designed system, it is the vast, vast majority of the time, it honestly feels like magic. It is the fastest way humanity has ever figured out how to find a needle in a haystack, because you're not even looking for it. You're just going directly to where the needle is. But we always have to remember the other side of that coin. Every single guess, every lookup, carries with it this small, but not zero, risk of being wrong, of leading to a collision, of taking you down that much slower path. Understanding that trade-off, that we are exchanging certainty and order for incredible probabilistic speed, that is the key to understanding the true power and really the elegance of the hash table.